In our most recent video, we introduced the notion of the polar coordinate system as an alternative to the more familiar rectangular coordinate system. In this video, we'd like to begin exploring what we can do with calculus in the polar coordinate system. In particular, we're going to talk about derivatives. Let's go to the whiteboard. I'd like to begin by asking you to take a moment to see if you can sketch the graph of r equals 1 minus sine theta in the polar coordinate system. I'll get you started. This is what the graph looks like in rectangular coordinates. And go ahead, stop the video and see if you can translate the sketch of that graph to a sketch of this function in the polar coordinate system. Okay, so let's do this together, and we'll see if the work here agrees with the work you did during your break. All right, so what do we have? This tells me that whenever the value of theta is 0, we're going to be 1 unit out from the pole. So let's call this a unit right here. And that's going to be one of the points on our graph. And then let's see, as theta moves toward pi over 2, theta is moving, as theta moves toward pi over 2, r is moving towards 0. So we're heading toward the pole, and by the time we get to pi over 2, we're going to be at 0. And keep in mind, that means that the pi over 2 line is going to be tangent to our graph. So it's going to look a little bit like this, perhaps. Okay. And then as we move from pi over 2 to pi, we're heading back toward 1 unit away from the pole. So there's a unit away from the pole. Again, we have vertical tangency at this point. So I'm going to be heading toward there, something like that. And then from pi to 3 pi over 2, I'm going to be heading from 1 unit from the pole to 2 units from the pole. So let's see, there's 2 units from the pole living there. So I increase till I get to something like that. And then between 3 pi over 2 and 2 pi, I'm back to 1 unit away from the pole again. And so it's something like this. All right. So let's ask a couple of calculus type questions about this graph. So what values of theta does the polar graph that we just drew have horizontal tangent lines? And then also, where does the graph have vertical tangency? Well, let's see, we can probably estimate a little bit. Looks like we probably have a horizontal tangent line maybe right there. Where was that? That was at 3 pi over 2. Looks like we have horizontal tangent lines, I don't know, somewhere between 0 and pi over 2. I don't know, the way I've drawn it, it looks like it's right about here. So whatever this theta line would be right here, perhaps, and corresponding point over there, it looks like it's horizontal tangent maybe about at that point, so whatever that theta value is. And then the vertical tangent lines looks like, well, actually, I think we're pretty sure we've got them at pi over 2, right? We already know that that what we usually think of as the y-axis in rectangular coordinates serves as a tangent line to the graph at this point, because that's where we were at the pole. So we can be pretty sure of that. It also looks like we have vertical tangents. I don't know. Is it here at at pi, or maybe a little further along, or I don't know. It's hard to tell. So I'd like to refine this graph a little bit by being able to answer these questions. I'd really like to know what these angles are. I'd like to know a little bit more specifically at what angle I was at another vertical tangent. Was it here? Was it a little further along? Hard to tell. So what does this mean? Horizontal tangent lines happen whenever the derivative, well, and here I'm thinking of how does y change with respect to x. Whenever I'm talking about horizontal tangent lines, that's a y against x question. Vertical tangent lines also is a y against x question. So I'm going to have to figure out how to think about derivatives. I'm going to have to think about derivatives of this polar graph, but I'm going to want to think about them as y against x, so dy dx. Somehow we're going to have to figure out how to answer that question. Well, I want you to remember something, right? If a point r theta in polar coordinates is described in rectangular coordinates as xy, then we have that x is equal to r cosine theta and y is equal to r sine theta. I think you probably remember that from the last time. Well, we're looking at the function r equals 1 minus sine theta. Well, if r is 1 minus sine theta and x is r times cosine theta, then it looks like I can describe my x coordinates as 1 minus sine theta times sine theta. And similarly, my y's as 1 minus sine theta times sine theta. So what I really have here is a way of translating my polar description of the function in terms of parametric equations. And we know how to find derivatives whenever functions are described or curves are described parametrically, right? We look at how y changes with respect to theta and how x changes with respect to theta, and that gives us dy dx. So I've carried out those derivatives here. You can check my work. In fact, I would encourage you to go back and kind of look at it yourself. Can you reproduce the derivatives just as a review of a little bit of Calc 1, and then come back and check to see that this is what you got. And I want to simplify this just a little bit because I'm going to need to work with it. Right, eventually I'm asking when does this derivative equal 0, and when is this derivative undefined? So I want to make these numerators and denominators a little bit simpler. And so we'll start here. So this looks like a good place to end the simplification. And so let's see, we're looking for where dy dx is 0. That's going to be where the horizontal tangency happens. And where dy dx goes off to either infinity or negative infinity, right? That's going to be where we have vertical tangency. So what's that mean? When is we have a fraction here. When is a fraction equal to 0? Well, if a fraction is equal to 0, then certainly the numerator is going to be 0. Whenever we're looking for the vertical tangency, that's going to be a place where the denominator winds up being 0. Now, there might be places where numerator and denominator are both 0. That's going to cause a little bit of an issue. We'll resolve that if we get to it. So let's start by looking at the horizontal tangent lines. And let's see, our numerator, look back again if you like. The numerator was cosine theta times 1 minus 2 sine theta. So if the derivative is going to be 0, that's going to have to be 0. Doesn't necessarily work the other way. Just because this is 0 doesn't mean this is going to be 0. But if this is 0, then That means my numerator is going to have to be 0. And I have a product there, so that means one of the two factors has to be 0. And a little trigonometry tells me that from cosine theta being 0, that's going to happen at pi over 2 and at 3 pi over 2. This equation can be re-expressed as sine theta equals 1/2. And you can draw an equilateral triangle and cut it in half to remind you where that happens. Let's call this length 1, that length 2. And Pythagorean theorem gives me that that's square root of 3. And so 1/2, so I'm thinking of that as opposite over adjacent. Well, this is the angle that's going to have 1 as the opposite side and 2 as the adjacent side. I'm sorry, opposite over hypotenuse is what I intended there, beg your pardon. And so this is the angle for which the opposite side is 1, hypotenuse is 2. And that was, well, let's see, these are all pi over 3. And so this is half of that, pi over 6. So theta is going to be either pi over 6 or 5 pi over 6, right? It's going to be the reference angle is pi over 6, and sine is positive in the first and second quadrants. So there you go. So if dy dx is 0, then theta has to be one of these 4 angles. For vertical tangents, let's see. So this was what my denominator looked like, and so I'm going to need to set it to 0. I'll tell you right now, it's difficult to play with trigonometric equations when we have multiple trigonometric functions involved. It's going to be a whole lot easier if we can write this entirely in terms of, let's say, entirely in terms of sine of theta. And that's pretty easy, right? Because cosine squared theta, we have an easy trig relationship, an easy trig identity that expresses that in terms of sine. And so if I simplify this a little bit, gather my sine squared terms together, my sine terms, my constants, then I have what looks like a quadratic equation in terms of the variable sine theta, right? So I'm thinking of a substitution here. Let's let u be sine theta, and then this becomes a quadratic equation. I can actually factor that the left side as 2 sine theta plus 1 times sine theta minus 1. And so one or the other of those factors has to be 0. And so that tells me that either from here sine theta is -1/2, or from here sine theta is 1. Let's see, where is sine theta equal to -1/2? Well, the diagram we looked at just a moment ago, it's equal to 1/2 at pi over 6. And so -1/2 is going to be reference angles pi over 6. And we're in either the third or the fourth quadrants. And so that's going to be at either 7 pi over 6 or at 11 pi over 6. All right. And sine of theta is 1 whenever theta is pi over 2. So looks like we have the answer to our question almost. The only problem is theta is pi over 2 whenever the denominator is 0, and it's also pi over 2, can be pi over 2 whenever the numerator is 0. And so we're still not sure what's happening. Now, I could go back to the picture and get a pretty good idea of what's happening. I mean, at pi over 2, we do know that I have a vertical tangent line. And so this one's going to turn out to be the one that wins out for us. But if we didn't know that, what we'd have to do, and what I'm going to do, is I'm going to look at the limit as theta approaches pi over 2 of my function. of my derivative. So I'm going to take this function, I'm going to look at the limit as theta goes to pi over 2 and see if we approach 0 or maybe positive or negative infinity, or maybe something entirely different. Let's take a look. So as theta approaches pi over 2, the form is 0 over 0. We just established that. Numerator was 0, denominator was 0. And so Bernoulli is going to come to the rescue for us, or as so many other people say L'Hopital. L'Hopital wrote the textbook which had the rule in it that we're about to use, but Johann Bernoulli was the one who came up with the rule in the first place, and so I'm going to use his name, give him the credit. And he says that if we take the derivative of both the numerator and the denominator and look at the limit as theta goes to pi over 2, we're going to get exactly the same. We're going to get exactly the same value. The limit's going to have the same value. And let's see. So I've done that. I've taken the derivative of the numerator, derivative of the denominator, and I'm not even going to simplify this. I can tell pretty quickly if theta is pi over 2. Well, let's see. Cosine of pi over 2 is 0. And so my denominator here is, let's see, 0 plus 0 minus 0. So my denominator is 0. My numerator, let's see, so this is going to be 0 right here. But let's see, sine of pi over 2 is 1. So in parentheses here, I have 1 minus 2. I have negative 1 times negative 1. So my numerator is 1. My denominator is 0. Well, that's undefined, but it has the form 1 over 0. And that form, any finite number over 0, is always going to give me a limit that's either approaching infinity or negative infinity, one or the other. And it's going to depend on the direction from which theta approaches pi over 2. But that's not even important to us, at least not in the context of this question. We know the limit approaches negative infinity or positive infinity, so that's going to guarantee that that my derivative, which is what this was expressing, my derivative is going to be undefined at that point, and I'm going to have a vertical tangent line. And so that's what we can conclude from that. So let's see. So do those answers agree with our picture? All right, so we can rule out pi over 2 here. We just established that we don't have a horizontal tangent line there, but at 3 pi over 2, at pi over 6, and at 5 pi over 6, we have horizontal tangents. Well, there's our 3 pi over 2, right? That one we were pretty sure of. And now we've established that it's whenever the angle is pi over 6, that looks about like this. Whenever the angle is pi over 6, that's about where my horizontal tangent line should be. So I need to refine that a little bit. And at 5 pi over 6, and let's see, so 5 pi over 6 is going to look about like this. So I'm going to have to refine it a little bit in order to make that the point where I have horizontal tangency. And let's look at the vertical tangency. Where did that happen? That happened at pi over 2, at 7 pi over 6, and at 11 pi over 6. Well, the pi over 2 we were pretty sure of, but the 7 pi over 6, that lives around here. So we're going to have a horizontal tangent. That's where the horizontal tangency is going to be. And so this is going to have to come out a little further. It's going to be a little more bulbous, and then we're going to wind up with a horizontal tangent there. At 11 pi over 6, the same thing's going to happen, right? So I'm going to have to come out a little further, a little more bulbous, and then that's where my vertical tangent's going to be, and I wrap back around. So let's refine that. Actually, I've already drawn a picture with those refinements. here it is. So, right, so we start at 1. I drew a little pi/6 line there, and I tried to force it so that that's where my horizontal tangent line was, right at about there. And over here at 5 pi/6, I did the same thing. So I have a horizontal tangent line there at 5 pi/6. Of course, at 3 pi/2, I have the vertical tangent here at the cusp point. And then I brought this out a little further, and at 7 pi/6, that's where I have my vertical tangent line. And at 11 pi/6, I have a vertical tangent line as well. Should be a little bit more symmetric, but you get the idea. And so there we have it. This graph is the polar sketch of r equals, whoops, that's not right, 1 minus sine theta. There we go. And so, tell you what, let's write in here I 1 minus sine theta calculus. Put that on a t-shirt and wear it around. Impress your friends. And that's how we can work with derivatives in the setting of polar coordinates. Until next time, stay safe, stay well. I'll see you then.